Hi viewers, welcome back to the second video on introduction to random vibration. So in the first video we established that most of the problems in mechanical vibration can be thought of as finding out the response against a given excitation, and depending upon the type of excitation the techniques are different and the type of vibration is also different. So we looked at few examples in the last video. I will briefly go through them once again. So the first example was that of a washing machine where there was a small eccentric mass little m, which was at a distance of capital R, and the washing machine was rotating at an angular velocity of omega. Then we came up with this mathematical expression where we told that the excitation force acting in the y direction can be written as mr omega square sine omega t. Omega t is this angle. Then the excitation will assume a shape like this. Everything is known. The time period of this particular curve is known. The amplitude of this curve is known. So this is a deterministic type of excitation. Then we went ahead to look at another example, that of a cam and cam follower. So here we have a system as shown here. This is the governing differential equation of this particular system. As you can clearly see here, the excitation force depends upon the y displacement. So y displacement is governed by this particular cam over here. It is rotating at an angular velocity of omega naught, and it has two peaks of displacements are r1 and r2. Now showing this in a curve or in a plot over here, I'm showing it here. From this it is pretty evident the maxima and minima are known, and what is the time period, that is also known, because we know all quantities. So here in this case as well, the excitation is completely deterministic. This particular term is deterministic, so the response will be also deterministic, the response will be also periodic. We will use techniques like Fourier series to solve this kind of problem. Then we went ahead and looked at the third example, that of a impulse excitation, where you had a jet engine and you need to find out the response of the engine against a bird impact. So this is how the mathematical representation will look like of that particular excitation will look like. It can be mathematically written like this using the Dirac delta functions. If you are new into Dirac delta functions, it is just a mathematical representation for representing a very high force at the time instant t equal to tau. So this f cap has the unit of the impulse. So when to give you an idea, if mass of the bird is mb and velocity of the bird is vb, then this particular f cap will be simply the product of these two quantities, or in other words, that will be the impulse transferred to this particular engine. So in this case also, even though the function looks a bit fancy, everything is deterministic. Then we went ahead and looked this case in which you had all sorts of trouble. So we wanted to study the response of a particular aircraft when it is landing. So the excitation on the aircraft will be a direct function of the displacement of the wheel. So we try to measure the displacement of the wheel, and the first assumption that goes into is that the wheels are rigid. I didn't mention specifically or this in the first video, but this assumption is pretty valid. We assume that the wheels are rigid, then we try to measure the displacement, then on 4 different days, and then we ended up with 4 different curves. So there was a lot of variation in the data, and we described the reasons. So since there were a lot of variation or randomness in the data, we told that description of the excitation function in terms of the time is not going to work, because we have different profiles on each day, so that is not going to work. So why is it so? Because there are a lot of dependent variables. I talked about tire pressure, temperature, wind conditions, how experienced is the pilot. So a lot of reasons. That's why we see a lot of variation in the data. Now what is the way ahead? So the way ahead is check whether excitation is having some kind of statistical regularity. Statistical regularity, how we can ensure a particular data set is having a statistical regularity, that can be quantified using averages. We will be looking into the different types of averages in this video. So this principle is very widely used in in mechanical vibration. Let's say if your excitation is varying like harmonically, then we assume that my response is also varying harmonically. We make these assumptions regularly. So extending that sort of a concept into random vibration, we will end up here, or we will have this. If excitation is having statistical regularity, then response will also have statistical regularity. So it can be also described using averages. So no more time description here. We will be describing both excitation and response in terms of averages. Then we begin this video with this very important question. Now, what are the averages? So we told that in order to make sure that the data is having some statistical regularity, we need averages. In order to describe both response and excitation, we need averages. So what are these averages? Let's have a look at them one after the other. To describe about averages, let me go back to the same example of that of an aircraft taxiing on a rough runway. So there are a lot of variables that affects the displacement of the landing wheel, which is assumed to be rigid. For example, on that particular day, what was the tire pressure and how talented the pilot was, and then what was the amount of payload that was carried by the aircraft, how was the wind conditions, and whether there was a change in the surface roughness characteristic of the runway, and all these things will influence. And finally we will end up with different plots for the displacement of the aircraft landing wheel if we make the measurements even for the same aircraft on different days. This clearly conveys the fact that this whole phenomena is a random phenomena. Given that this is a random phenomena, before we move further, let me give you a few formal definitions. Let's say I have a collection of these plots, collection of these time plots as shown over here. Let's say this is corresponding to the first day, this one corresponds to the second, this one corresponds to the third, and let's say I have some capital N number of them with me. So each of these curves are called, or each of these individual time histories are known as a sample function, as shown here. And generally the variable xk of t, where k varies from 1 to capital N, this is known as the random variable. So this individual time history is known as a sample function, and the variable sk of t is known as a random variable. And the whole and the entire collection of all possible time histories, that is known as a random process. It is usually denoted as sk of t using this curly brackets. This conveys the set of all individual time histories. That is what a random process is constituted of. So we saw that excitation is a random process. For treating it mathematically, we need to establish that excitation, or the displacement of the landing gear in this particular example, is having some kind of statistical regularity. For ensuring that, we need to compute some averages over these n sample functions. The first average I'm going to talk about is ensemble average. First ensemble average is just a mean. First, let me define it mathematically. So, Mu is a symbol we usually use for averages. I'm defining it at a time t equal to, let's say, tau. Then mean is defined as 1 by capital N. Let's say I have n sample functions. Each sample function is an individual time history where summation goes from 1 to capital N. You are summing the individual values at t equal to tau. For example, let's say tau equal to 5 seconds for this particular example. Then 5 seconds into landing, let's say for this particular time history, I am seeing a displacement of x1 of tau. x1 of tau, let's say that is equal to 5.02 mm, slightly on the higher side, but for example's sake, or for the sake of explanation, let's say x2 of tau was coming around 4.8 mm, as shown over here. X2 of t, I'm drawing this perpendicular, and this perpendicular is meeting this curve, and then I'm drawing a line parallel to the time axis to compute what is the displacement of the landing gear in this particular time history for corresponding to a time equal to tau. Similarly, let's say my x3 of tau was coming around 5.2 mm and x4 of tau was coming around 3 mm. So on an average, we can see 5 seconds into the landing, I am more or less seeing a displacement around 5 mm for my landing gear. Or in other words, here in this example I took 4 example, but let's say I have capital N examples where capital N is sufficiently large, and then this mu x of t equal to tau, mean at per time instant t equal to tau, is assuming some recognizable limits, then we can say that excitation or the displacement of the landing gear is showing some amount of statistical regularity. Now let's move ahead to a next type of ensemble average, which is known as autocorrelation function. Autocorrelation function is another ensemble average where you take the product of the values of the displacement of the landing gear at two instances of time. While computing mean at a particular time instant t equal to t1, we simply summed or took the summation of individual values sk of t1. But while computing autocorrelation function, we are taking the product of two values. One is sk of t1 and xk of t1 plus 2. So you take one individual time history and you evaluate what is the displacement of the landing gear at t1, and you compute the displacement of the landing gear at a later instant t1 plus tau, where tau is a real number, and then you compute the product and you do the same for all n individual time histories, then divided by capital N, which is the total number of sample functions that we have got. Then you will end up with a number called autocorrelation function. So this is a second order average. It's a higher order average, you can say, compared to the mean. Similarly, you can define third order averages and fourth order averages as well. So in essence, we have looked at two kind of ensemble averages. First is the mean, which is defined at time instant t1. I missed out a certain thing here, which is this particular thing, which is limit n tends to infinity. That means you should have sufficient number of examples before you say the mean at this particular time instance is this much. You should have sufficient number of examples with you, or sufficient number of time histories with you. The same holds true for autocorrelation function also. There is a limit n tends to infinity term that should be included, which conveys that you should have sufficient number of sample functions before you say at this particular time instant my autocorrelation function is this much. So these are the two ensemble averages. To briefly sum up what we have seen in this video, once again we relooked into the very essence of random vibration, how it is different, and then we went through some formal definitions of a sample function, then what is a random process, or a stochastic process, and then what is a random variable. Definitions were seen in this particular video. Then we went ahead to talk about the relevance of averages for a mathematical treatment of random vibration, and we then went ahead and defined two ensemble averages. They are called ensemble averages because the average is taken over different samples. As you can see here, the summation goes from one individual time history to the capital Nth individual time history. We looked at mean defined at a particular point time instant t1, and we defined the autocorrelation function also. Thanks for watching.